Section 1.7 is all about solving inequalities. So when we're solving an inequality, the process, what we're doing is we're finding the set of numbers that make the inequality a true statement. So for example, x is less than 3. That's an example of an inequality, right? The difference is there was way more than one number that could satisfy that equality, right? All the negative numbers would satisfy that inequality. So would 1 and 2. They'd all make this a true statement. So the set of numbers that make x less than 3 a true statement is called the solution or the solution set. And we say that any of those numbers satisfy the inequality. So when I have an inequality, so let's say, for example, x is less than 3, and I want to graph this on a number line, I know that 3 is not in my solution set, right? Because 3 is not less than 3. When we have less than or greater than, the endpoint is not included in our solution set. So we're going to denote that with a parenthesis. So here my solution set is x is less than 3. So here's a parenthesis. It should go this way. And I shade everything less than 3. I'm going to write my solution in interval notation because I don't always want to draw a number line, although they're very helpful when it comes to determining your solution. So this would be the solution from negative infinity, which always gets a parenthesis, to positive infinity. So to positive 3 with a parenthesis because my endpoint is not included. So we use parentheses to represent endpoints that are not solutions. Sometimes that can be graphed as a hollow dot on the number line. Sometimes it's graphed like a parenthesis, but we use this with less than or greater than. Square brackets indicate that our endpoints are solutions. We use that with greater than or equal to or less than or equal to. So if I had x is greater than or equal to 2, and I wanted to graph that on a number line, I could write that as a solid dot, or I could put a bracket there. And I know that x is greater than or equal to 2, so 2 would make this a true statement. That's why 2 is included, because 2 is greater than or equal to 2. I shade to the right. So I can write this in interval notation. This is from bracket 2 all the way to positive infinity. So that's how we write our graphs in interval notation. If you aren't certain how to write something in interval notation, I always recommend, sketch it out just to make sure your solution makes sense. If your solution's all real numbers, you can write from negative infinity to positive infinity. If there's no solution, you can write this. This is the empty set. So here are some other, here's a table comparing what the inequality looks like and the graph. If you had any questions on the different types of set notation you can come across. So inequalities have some interesting properties. So the first is the non-negative property. Friendly reminder, we're just working with the real numbers here. So if I square a negative, it's always going to be a positive. So for any real number, a squared is going to be greater than 0. So a squared is positive. What's nice about inequalities like equations, I can keep them balanced if what I add to one side I add to the other, or what I multiply one side by, I multiply the other side by. So these are some properties of inequalities. So in order to solve a linear inequality, you treat it like it's an equation until it comes to the solution set. So the first thing you're going to want to do is simplify your algebraic expression on each side. Next thing you're going to want to do is collect all the variable terms to one side, isolate your variable, and solve. The only thing that's a little different, I highlighted in orange here, right, is that you need to change the sign of the inequality if it has a negative variable when you multiply or divide by 1. You've got to change the sign. So less than would become greater than, less than or equal to would become greater than or equal to, and so on and so forth. Lastly, you need to express the solution set in interval notation. Graphing the solution set on a number line may help. So let's work through a couple of examples. I have x minus 7 is less than negative 12. So I'm going to add 7 to both sides. I have x is less than negative 5. Oh, look, a beautiful number line. I'll put number 5 in the middle. I'm going to go ahead and graph my solution. I know my endpoint is not included, so it's going to be a parenthesis. I have that x is less than negative 5. Well, negative 6 is less than negative 5, so I'm going to highlight to the left. So my solution would go from negative infinity to negative 5. Parentheses. Next, I'm going to solve the inequality. 1 is greater than 3 minus 5x over 2, which is greater than or equal to negative 7. I'm going to go ahead and multiply both sides by 2 and the middle as well because I want to get rid of this fraction. That gives me 2 is greater than 3 minus 5x, which is greater than or equal to 14, negative 14. I'm going to subtract 3 from both sides. I get negative 1 is greater than negative 5x, which is greater than or equal to negative 17. I divide everything by negative 5. I get 1 is less than x, which is less than 17 fifths. That's like 3 and 2 fifths. So we've got 0, 1, 2, 3. This is 1/5. So 1/5 right there. Its endpoint is not included, so it gets a parenthesis at 1/5. Then at 17 fifths, which is like 3 and a bit, the endpoint is included. So my interval is parentheses 1/5, comma 17 fifths bracket. Some inequalities with unusual solution sets are given below, right? So we've seen equations that have no solutions or infinitely many solutions, and this is also true for inequalities. So for example, I have x is greater than x plus 1, and this has no solutions. The reason why is because it's true, there's no way you could have a number that's greater than itself plus 1. Also, if I went ahead and solved for x, I'd get 0 is greater than 1, which is a false statement. So if it's a false statement, there's no solutions or an empty set worth of solutions. This next example has infinitely many solutions, and let's see why. So I've got 3x plus 3, and then I can combine like terms. It's greater than or equal to 3x plus 1. If I subtract 3x from both sides, I get 3 is greater than or equal to 1. And this is a true statement. This is always going to be a true statement regardless of whether x equals square root of 2, x equals 4, x equals negative 10 to the 15th, you know. Any number is going to make this a true statement. So it has infinitely many solutions, which we'll write from negative infinity to positive infinity, or you could write out infinitely many solutions. It's up to you.